So I'm a planetary geologist, and one of the planets I care about is Mars. And specifically, I care how old Mars is. And there are a couple of ways you can go about doing this. And one way is you can look at Mars from orbit, look at the craters and count them and get a sense. And when you do this, we think that Mars is at least 1 billion years old, so really old. Now, the other way you can do it is to measure some Martian rocks and get an age using radioactive decay. In this case, we're going to use the elements potassium and argon. So the way this works is when the rock forms, it has some potassium in it. It captures that potassium in the crystal lattice. And over time, some of that potassium is radioactive. And it's going to change or decay into argon. And this sets up a little clock, like an hourglass. When it starts, all the potassium's in the top. And over time, it's going to decay to argon. So all you have to do is measure how much argon you have, and you can calculate back how old this is. So when we do this for the Martian meteorites, we get an age that's surprisingly young, 250 million years old or so. And yeah, yes, I did just say that 250 million years is young, but compared to our expectation that it's over 1 billion years, that is young. So this sets up a sort of problem. And one way people have thought to explain this is that maybe there's something wrong about that radiometric age. One of the requirements when you do this kind of work is that it's been a relatively calm environment since the rock formed. Because argon is a gas. It doesn't like being in the crystal lattice. It likes to be out in the atmosphere. So if you disturb it or heat it up too much, you'll lose some of that argon. Think back to the hourglass. If you were to take some of the bottom sand out of this, it wouldn't show you a real representation of how much time's there, because you've lost some of that. So here's where the work that I do comes in. I'm actually testing this, because one of the things about these Martian meteorites is they're by definition not a calm process. They got to Earth after something slammed into Mars and blasted it here to Earth. So maybe it's reasonable that slamming an asteroid into a planet could mess up the argon. But we've not really tested it before. So what I'm doing is looking at rocks here on the Earth where we know what the age was to begin with, and we know independently when the asteroid hit, so we can measure it and see. Now, of course, I'm still working on this, but the initial results look like the answer is no, it actually doesn't mess up the argon, which is really cool, because what that means is that these ages of Martian meteorites are probably right, and therefore Mars might have been active geologically a lot more recently than we thought. Thanks.
So is Mars older than your mom?
Some of it probably.
Yeah, I know, that was terrible. Right after Mother's Day, she said. Hopefully Mom's not watching right now. So I'm curious, you said, you're working on this, and you described the loss of argon when the meteorites slammed into the Earth. So how exactly are you testing this? Are you going out and like slamming rocks into the ground
Right.
and then check? What do you do?
So I'm working with rocks from an impact crater up in Canada called Manicouagan Impact Crater. And that's nice because we have a whole suite of rocks there. Some that are just the normal rocks that are background, so we can get an age of what it was pre-impact. And then some we have that actually melted and created a new rock. And that tells us, since it's a new rock created at the impact, that would be the time of the impact. Then there's this third that was slammed into but never melted. So I'm looking at that to see which age does it match. Does it match the time of impact, or does it match the original age?
Okay.
Okay, I have a slightly less silly question. So what's your thought on why it doesn't reset? I mean, my sort of very crude knowledge of this is you would expect it heats up, the argon being a volatile gas is going to diffuse out, and it's going to mess up the clock. So why do you think maybe that doesn't happen?
I think it's an issue of time. The two things that are really important for resetting of the argon is temperature, but also time. And these impacts, while they're really warm and really hot, they just don't last for that long. And so I think it's just an issue of not enough time.
I don't have a question. I just wanted to say that's a lovely demonstration of radiometric dating. That's so much easier than all those parent-daughter calculations. I love it.
That's why I'm not a mathematician. I'm a geologist.
Thank you.
Thanks, Stephen.